Okay, so now that we've kind of looked at glaciation and how it changes the surface of the Earth, we're going to look a bit more at how the climate itself has changed in the past to allow for these massive glaciations that we've seen, right? Because obviously the Earth's climate is changing. If I told you in the last topic that Alberta used to have glaciers kind of going everywhere, right? And that's why we see erratics and drumlins and all those features. So today we're going to look at what's an ice age, okay? And then we're going to look into how we know a lot of this stuff, which is through the idea of an ice core, okay? So what is an ice core? When studying an ice core, how do we know how far back we are looking in time, okay? How can ice cores tell us about the ancient atmosphere? And how can ice cores tell us about ancient temperatures? Ice cores are important today, if you can tell. Okay, so like we said last time, right, there was a lot of glaciation in Earth's past. A lot of our land features actually come from these glaciers forming all over the Earth, forming, advancing, melting, and repeat. Okay, so why was there so much? Well, the Earth's climate has fluctuated throughout its history. We'll get later into why what's happening now is different, but there have been natural fluctuations in the Earth's history, right? You can kind of see here is a graph of the Earth's temperature as a function of time, right? You kind of have these cool periods, cool, warm, cool, warm. And notice the time scale up here, right? We're talking over millions of years. And I bet you're probably saying to yourself, how could we possibly know the temperature of the Earth 570 million years ago? Well, we have a pretty good way of estimating it, and we'll talk about that in a second here. So that term ice age, you kind of hear it thrown around, and what do you think? You think, oh, it's cold, right? Or you think of a woolly mammoth and a saber-toothed tiger, okay? Well, yeah, it's cold, but there's a little more to the definition than that, right? Fort McMurray does not enter an ice age every winter, even though it might feel like it. For the Earth to be in an ice age, okay, what has to happen? So obviously, it's a long period of reduction in the temperature of the Earth's surface and atmosphere, okay? But what makes it an ice age and not just kind of a cold winter? Well, it's the presence or expansion of continental and polar ice sheets and alpine glaciers. Okay, so in other words, there's widespread glaciation. There's glaciation in places we usually wouldn't get it, right? Like we'd always kind of expect it to have it the North and the South poles. However, this is talking about ice sheets farther south or farther north than you would usually expect them. That's what makes something an ice age. The most recent ice age we've been in was actually it ended about 10,000 years ago. So, how do we know all this stuff? Because this seems kind of crazy that I could tell you what the temperature would probably look like on Earth even 1,000 years ago, let alone tens of thousands of years ago, let alone 500,000 years ago, right? Well, we have this awesome tool at our disposal called ice cores. Okay, so I'll just quickly run you through what an ice core actually is, how it works, how it tells us stuff. Okay, so in places where snow doesn't melt in the summer, it builds up and compacts into layers. So the snow doesn't melt and it builds up and compacts into layers, right? Well, that makes sense. If the snow doesn't melt and then winter comes again and it snows again, right? Now you've got layers of snow, which means if we can see the layers, then for each layer, we're going back 1 year, right? We see there's one winter. Okay, there's the previous winter, there's the previous winter, there's the previous winter. So by counting back in layers, we count back in time. It's kind of like if you've ever counted rings on a tree, right? If you cut down a tree and count the rings, you can count how many years it had because it grew in the summer and then didn't in the winter and then grew more in the summer and you get those rings showing up. Okay, so it's like counting rings on a tree. Now, great. Okay, so that lets us know how far back this ice formed. What useful information is contained in that ice? Well, we can actually look at what the atmosphere was made of at the time that ice froze. So we can study the composition of the atmosphere at the time when that snow fell or when that ice formed, because when it melts, it traps little pockets of atmosphere in it. There's little bubbles of that atmosphere trapped in the ice when it gets compacted into layers. So we look at gases that are trapped in the ice. It's literally ancient air that's kind of been preserved for us in the ice. We can even do better than that. Not only can we tell what the air was like, we can actually tell how warm Earth was. We can determine Earth's temperature by looking at the isotopes in water molecules. Okay, so that sounds pretty complex. What you need to take away from that is basically, depending on the temperature of the Earth, different types of water molecules will exist. So some will have more neutrons or less neutrons than the other. If you think back to our chemistry unit, right? An isotope was just something that had the same number of protons, but a different number of neutrons. That's essentially what we're talking about here. And it turns out in water, we can study this very well, that depending on the temperature of the atmosphere, water will exist in different isotopes. Okay, so by looking at the water that's in that ice, we can say, it looks like the Earth was about this warm because it has more of this isotope or less of that isotope or whatever it might be. Okay, we can also even tell major geologic events that might have happened the year that that snow fell, right? So the example they give is that maybe there's a layer of volcanic ash in the ice, right? You get kind of a black layer of ice and you look at it and you see it's volcanic ash. Well, what do you think that means? Probably there was a big volcanic eruption that year, right? The year that that snow fell and that ice formed. Okay, so these ice cores have actually provided really strong evidence of not only this past glaciation, these drops in Earth's temperature or rises in Earth's temperature, but they also show a very clear link between greenhouse gases, which we'll talk about a bit tomorrow, and rising global temperatures. So remember how I said we could see what the ancient atmosphere and the ancient temperatures look like? When the atmosphere has more carbon dioxide, guess what happens to the temperatures? They go up. Okay, when the atmosphere has less carbon dioxide from the ice core, well, the temperatures from that layer are also lower. Okay, so there's not only can we kind of study now the link between carbon dioxide and temperature, there's a strong correlation between it throughout the Earth's entire history. So just kind of connecting those 2 points to this point here. Show you a quick video of how we actually kind of analyze a ice core.
This frozen library, the National Ice Core Lab in Denver, Colorado, has ice from all over, kept at minus 35 degrees. The oldest core here goes back some 400,000 years. Here, really ancient ice from Greenland in the north and Antarctica in the south reveals Earth's climate history. Let's see what cores like this can tell us. First are those layers I mentioned in the New Zealand snow. They've turned to ice and we can count them. Summer, winter, like tree rings, we can date the core. Other cores tell other stories. Look at this. It's the ash of an Icelandic volcano that blew up to Greenland 50,000 years ago. Cores hold other and even more important secrets. Look at these bubbles. They formed as the snow turned to ice and trapped old air that's still in there. Scientists now are working with cores from Antarctica that go back even further. They tell us with a very high degree of accuracy how much carbon dioxide was in the air that far back. Researchers break chunks of ice in vacuum chambers and carefully analyze the gases that come off. They're able to measure very precisely levels of carbon dioxide in that ancient air. Looking at the cores, we see a pattern that repeats. 280 parts per million of CO2, then 180, 280, 180, 280. By analyzing the chemistry of the oxygen atoms in the ice, you can also see the pattern of rising and falling temperature over time. Colder during the ice ages, warmer during the interglacial periods. Now put the two lines together and you can see how closely temperature and carbon dioxide track each other. They're not exactly alike. At times, the orbits caused a little temperature change before the feedback effects of CO2 joined in. But just as we saw in New Zealand, we can't explain the large size of the changes in temperature without the effects of CO2. This is the signature of natural variation. The cycle of the ice age is driven by changes in Earth's orbit, with no human involvement. But here's where we are today. In just 250 years, since the Industrial Revolution, we've blown past 380 with no sign of slowing down. It's a level not seen in more than 400,000 years, 40 times longer than the oldest human civilization.
Okay, so really quite an incredible scientific tool, right? That we're able to get this history of the Earth's atmosphere, its temperature, and even know how old it is by looking at these ice cores, right? See, you can see the layers in here, right? Notice how there's kind of these bands, right? So we would count back, look at the atmosphere that's trapped in there, look at the water molecules to find the temperature, and then count back to see what time frame we're roughly looking at. So just looking now here at the last ice age, the last time that there was widespread glaciation, when glaciers covered land much further south than they do today all the time, right? So like most of the northern hemisphere. Okay, so the last one is often called the Wisconsin glaciation, just because we first kind of found it because we kind of first started studying it in Wisconsin. But happy coincidence, you might know Wisconsin's about there. So it could have been called the Wisconsin glaciation because ice went down that far. Okay. So this only ended about 10,000 years ago. And you can see during that Wisconsin glaciation, during this last ice age, most of North America was covered in an ice sheet, a huge ice sheet, right? You are here, or you are today, right? You're right there, roughly. That's Fort Mac. Okay, look at us. We would have been under kilometers of ice. Literally kilometers of ice would be above your head right now if you were standing right where you are 10,000 years ago. Okay, pretty wild to think about. That's how much Earth's temperature changed. You got to remember, did it look like this in the summertime, right? I know we like to complain about the winter here, but could have been worse, right? Could be like this. It's a glacier, it's permanent. So even in the summertime, this massive sheet of ice was there, okay? And like I mentioned earlier, okay, the Great Lakes, Great Lakes are a bit of melted Laurentide ice sheet, which is just the name for this massive ice sheet that kind of covered us, right? So you kind of see the progression here. 21,000 got a little colder, ice advanced, right? Little warmer, ice starts to retreat, but thousands of years are going by here, right? It's not summertime, it's thousands of summers are going by, okay? And then about 5,000 years ago, well, that starts to look like what we know now, right? Greenland is covered in glaciers even today, not completely covered, but it does have a lot, right? So as we go, it gets more like this. And those Great Lakes, they're kind of the last remnant meltwater of this incredible glaciation event about 10,000 years ago. So this has happened many times throughout the Earth's history. This is just the most recent one. Okay, so that actually wraps up topic 2. Okay, so the big ideas you should be able to answer now, or hopefully, if not, just go back and see if you can find them. Okay, what is an ice age? Okay, the proper scientific definition. What is an ice core? When we study an ice core, how do we know how far back we are looking in time? How can ice cores tell us about the ancient atmosphere? And how are they able to tell us about ancient temperatures? All right, if you're looking for practice with topic 2 stuff, check the topic 2 section of the practice assignment for this week. Okay, again, that's in the Google Classroom or on the agenda.